Hi guys, thanks for joining us here physically at SIA, and for those online, thank you for tuning in as well. So today we have with us Ramboll. So they're quite a big name in the industry. I'm sure most of us will have heard of them, and they'll be talking about some of their tech-enabled capabilities. And yeah, I'll just leave it to them. So this is part of an SIA series on Tech Talks. This is the part 2 of 6. So I think every month we're gonna have one. Um, yeah, stay tuned and follow us on Instagram or Telegram or whichever lah, and we'll keep you updated. Yeah, and so after this session, we'll just have I mean, the space is open for networking. You guys want to talk to them, exchange questions or discuss amongst yourselves. That's cool. Maybe we can about half an hour, and then we'll have to close out the premises. Yeah. Okay, so I'll just hand the time over to Rambo. Thank you.
Okay. All right. Can you hear me? Yeah. All right. Okay. First of all, thanks for having us here. Obviously, we are an engineering firm. We're not an architectural firm, but we are very happy to be here to share what we do with you. So our presentation today will guide you through a little journey, which consists of 3 steps. The first one is a little bit introduction of who we are and why we do what we do and how we do it. The second part is more about sort of a digital workflow that we would do in a typical project that we work on. And the third one is an actual case study that my colleague here, Sam, will talk to you about a little bit more in details. So a little bit about Ramboll. Ramboll is a Danish company headquartered in Copenhagen. And we have offices essentially everywhere with about 17,000 employees worldwide. So it's a very big company, mostly on engineering consultancy. Um, but obviously we are located in Singapore, so we are the regional headquarters, Asia Pacific headquarters. We are in 100 Amoy Street, so if you pop by, you're welcome to come in. We have a nice cafe at the first floor. In Within that office, within the Rambo building here in Singapore, there are different markets, but we're part of the building markets, which essentially consist of engineering services like civil and structural engineering. So we go by quite a strong design ethos. I would like to think that that's one of the thing we are most famous about, which is quite a strong design ethos. We do our things around redefining engineering excellence globally because we work globally through innovation and regenerative design. So I hope that by the end of the presentation, probably you get this statement a little bit more. Now, when we look at a map of the world as a unit here in Singapore, our office, we did about 800 projects in the past 25, 26 years, everywhere in the world essentially, although most in the region, in the APAC region, of course. And we have been very lucky to work on several things, like from high-rise, mixed development, some smaller scale projects, some research stuff with university, any sort of thing. So we give the same level of importance and priority to the same projects. That's sort of our approach to design. Now, when you look at the building market, I was explaining earlier, it's essentially mostly formed by civil and structural engineering service. We do also environmental and sustainable design, EST, and we do some smart technology, so the application of smart technology in the built environment. And we're building up a couple of teams on facade and MEP as well. So these are the services that we have under our roof. But we have a sort of binder that tries to bind all of these independent disciplines together, and that's what we call Future Design Studio. So the Future Design Studio is myself, Sam, and other 6 or 7 colleagues. So we are a little unit that tries to bind all of the disciplines together by pushing the boundaries of design. Now, Future Design Studio, so what do I mean by it? What is it? How do we do it? Well, first of all, it's, as I just said, we're about 8 to 9 people, so it's a relatively small studio. And we focus on computational design, but we are formed by a group of people that comes from different backgrounds. So some are architects like you are, some are computational designer. We have some structural engineers, data scientists, etc. So the idea is to have people from different backgrounds so that we get the benefit of different skill sets essentially. And as the team will grow, we'll obviously will want to push and have different different specialties as well. Now, where are we coming from? Like, what is our objective? I think our goal, and I know it's a little bit ambitious, but bear with me here, is to try and bridge the gap that there is, historically speaking, between architecture and engineering. So there's always been that dichotomy between architecture and engineering. So we try, or at least we aim at bridging that gap. So that's what we want to do, bringing the architecture and the engineering closer together. And we think we want to do it on two levels. One is communication. So it's a simple thing, just sitting in a room together with the architect that we work on a project, co-create things, brainstorming and thinking, sharing ideas and understanding. So that's really the first simple approach. The second approach is technology. So we apply all our computational thinking and design, technical capabilities, digital workflows, etc., to enhance the design, to bring it to a higher level of quality. So through communication and technology, we think, or at least we hope, that we can sort of bridge that gap that historically there is between architecture and engineering, and that's where we sit. Sort of that's where we try to do the best of our work. Now, how do we do it? So that's the goal. So that's what we try to do. But how do we do it? We do through computational design, essentially. That's one of the key things that we do. So computational design, which obviously means that we leverage the technology, every kind of latest available technology, to enhance our capability. So we want to augment ourselves, essentially, to do things better, to do things of a higher level of quality. And design, so which means obviously bridging that gap, right? Bringing engineering solution closer to the architectural design intent. So that's sort of how we tend to do it. These four are our vision. I think we recently came up with this with a few vision or goal that we have. FDS, I mentioned, is the name of our group, which is Future Design Studio. So what do we think that future design should look like? We discussed about it as a team, and we came up with this sort of idea that the future of design should be clear, it should be efficient, empowering, and pioneering. So clear, what does that mean? Clear means that it is essential to communicate things clearly between engineering and architects so that we can have a clear understanding of what we do, and even with our clients, with our developer. So to do that, we apply some geometrical rationalization, for example, or we put a lot of effort into visualization. So when we do our design, our presentation, our report, our drawings, we really want to make sure that the things we do are clear, understandable. And we also put a lot of emphasis in rationalizing geometries. When geometries are too complex, they are hard to be built, so we want to rationalize it while maintaining the design intent that you have. So that is one of the vision. The second one is about being efficient. Obviously, there is a lot of emphasis nowadays around sustainability. So being efficient is always been essential. Now it's probably even more. So being efficient means that as structural engineers, we would want to optimize our structure as much as possible, optimize the geometry of a system as much as possible, because that brings us to a place where we can save material. By saving material, we can save money for our client, which is great. But even better, we can save carbon. So we don't have we can reduce the embodied carbon in the atmosphere. So we do that through some topological optimization, form finding, and other means. So we use computational tools to achieve our vision. The third vision that we have is empowering. So by empowering, we mean that we think that the future, or the design in the future, should empower the designer. So we want to feel empowered. We don't want to waste time in doing repetitive things. We don't want to waste time in doing boring things. We just want to do creative things. So we want to use computational design to bring us there, to empower ourselves. So how do we do it? Again, we try to enhance engineering workflow. We work a lot in software interoperability, so we don't have to spend time in jumping from one platform to the next. We create little plugins or script that help our engineers to optimize structures and do their engineering works better. And the last sort of vision that we have for the future of design is for it to be pioneering. That's in the name itself, is the future of design, so it has to be pioneering. So what do we mean by it? For now, we're focusing a lot on artificial intelligence and prototyping. So artificial intelligence for us is very important to explore. So we adopt some of this cutting edge technology like multi-objective optimization, topological optimization, etc., into our design. But at the same time, we do also a lot of prototyping with university, working on new material, new structural typologies, etc. So you get a little bit of a overview of essentially what we do and how how we through those things that we do, how do we achieve our vision, or at least how we try to achieve our vision. Obviously, as the team will grow and as we will progress over time, we will have more visions and more things that we're capable of doing. But for now, that's sort of where we are with it. So that was a little bit of an introduction of who we are and what we do. But as I say, the second part of the presentation intends to jump in a little bit more of a detailed workflow that we typically would have in our daily life. So when we look at a project, life of a project essentially goes from pre-concept to concept design up to construction and beyond. So these are the normal stages of design. So where do we sit as a computational design team, as a future design studio? Well, we can say that essentially we go from concept or sometimes even pre-concept up to tender design. So that's where our influence is. But we think that within these processes, mostly we would bring a lot more benefit during the computation, the concept, sorry, and the schematic design. Beyond which, detailed design, tender documentation, we still bring benefits, but perhaps not as much as we would at a concept stage. Concept and schematic is where we can really work with the architect to change geometry and emphasize on geometrical optimization, etc. So that's where the core of our work tends to be. Now, when you look at that workflow, you see kind of what the normal steps of a design process would be. So we receive typically a model from you, a form of design, sometimes just a sketch or scribble on a paper, or sometimes a physical model, and we take that on. We take that on and we create our geometrical model. We create a geometrical model, which is supposed to be a structural model. So essentially, we take your design intent, we rationalize it, and we create a structural model from it. Then we go into what we call optioneering. So we study a lot of design options, variation, different structural options, and we share that with you so that we have that conversation. And you might like some more than others. The client would like some more than others, and then we can select and downstream that. After the optioneering, essentially from a number of options, we then sort of shortlist it to a finite number, sort of a smaller number, 2, 3 options. And that's when we start the design refinement. So that's another stage. Design refinement for us means essentially optimization. So we start to go into the detail of optimizing things, removing things where we don't need them, reduce the amount of material, collaborating with you in that process. Once that is done, we then have a solution, a structural system, and we move towards the detailed design stage where we have to develop details like, more detailed things like connections and get it to the next level of resolution. And ultimately, standard documentation, drawings, models, etc. But you notice that the bar chart, I think, yeah, up here, the beam model and drawings or report, essentially, it's from a schematic stage up until the end of the project because we need to create beam model at a schematic stage, and we have to continue developing it and improving it as we move into our design. So if we bring that sort of digital workflow, if we look at that digital workflow, how do sort of our software capabilities and our digital capabilities apply to that? So at the beginning, as I said, we would receive a series of models from you. Sometimes they're in SketchUp, sometimes there's just a PDF sketch or something. Sometimes, and most recently, it happens that we tend to receive more Rhino models, which is a good thing because we love Rhino, so we do everything in Rhino as well. So we take your model and we understand it, we rationalize it. So we work within Rhino and of course Grasshopper and the whole Zoo family. And we have a whole sort of environment and ecosystem of softwares that we use and applications that we use. But we are within the geometrical modeling. So if you look at the title up there, this is still a geometrical modeling. There is no structure analysis in it yet. Typically, our structural analysis would be separate. on other platform, on our other softwares, we would do finite element analysis, and that would be a separate set of analysis. But through some internal script, we managed to include that into our workflow. So now finite element software becomes part of the same workflow. So we can very flawlessly move from a Rhino, a geometrical model, to ETABS, which is our finite element software, very easily. So that is really an enhancement for our workflow because we can do things a lot faster, a lot better. Not only geometry, parameterization, etc., but also actual analysis and design. Obviously, after we have an ETABS model, we would do into the detailing things and we would end up on a Revit platform. We need to do a model. Again, typically that would have been a separate set of people, a separate set of hours and time dedicated to create a separate model. But we spent some time with the team and we also tried to bring Rhino within that workflow and through a couple of applications, we managed to bring that in. So there is that whole process now, a very seamless workflow, which my colleague here, Sam, will explain to you on a case study later, that allow us to move from essentially a geometrical model that you give to us with architectural design intent to rationalization and parameterization of it, an actual analysis where we manage to find sizes, stresses, and forces to a final model. And once we have the final Revit model that is shareable with everybody, with our client. So that's a whole sort of workflow, a digital workflow that we created and is applicable to all our projects from day one to the end, to the actual documentation. And obviously, at any time we can export in whatever type of software people needs, whether some people still needs AutoCAD, so we give that to them, or PDF or SketchUp and stuff like that. So that can happen at any time. So these kind of workflows is applied to all our projects, and obviously it's an incredible digitalization that I think we brought into the processes that help us not only reduce the time that we have to waste on projects, um, but also it gives us time back to focus on creative things. So that is what I meant at the beginning of one of our vision about being empowering our designer. This is doing that. By using these workflows, we can empower our people. They don't have to build every time a new model, but we can do it seamlessly, essentially. So enough said on the introduction and the digital workflow, and now Sam will share with you an actual application of a digital workflow where we use some artificial intelligence and multi-objective optimization on one of our projects. Sam, there you go.
Check, check. Okay. Good evening, everyone, and thanks, Giovanni, and everyone for the opportunity for us to be able to like showcase a little bit of what we do and our vision. So now I'll go through one case study, which essentially go through the digital workflow that Giovanni has introduced to us previously. So our case study is gonna be this stadium, and in particular is gonna be the roof structure of it. It's a long span roof structure. And then at the top of the screen, you can see the workflow map, and we can use that to keep track of at which part of the design we are currently at and what part of the workflow and what kind of tools we are applying to the different kind of design stage. So let's take a closer look at the shape of the roof itself. It's quite a big roof. The middle cross section is about 250 meters, and the side cross section is about 200 meters. And in terms of the general shape of it is a dome. But then if you take a look at the front elevation, the dome is faceted into three main zones: the side slope and the middle curved loft. So after we received the architectural intention model from the architects, then we came up with a few structural systems that can be applied to the design. So we came up with a few different structural systems like one-way trusses, two-way trusses, and their variations, and also compression ring systems. And then after a series and rounds of discussions with clients and architects and among ourselves, we decide to move on with option 3A, which is the two-way trusses, arch with tension ring. So the main feature of this design is the two set of arches that crisscross perpendicularly, and then these four trusses are tied together with tension ring around it. And then after we finalize our structural systems, we move on to actually optimize geometrically to find a shape that is going to perform best while maintaining this kind of structural system. So design optimization itself is a very broad topics, and it might seem daunting for us architects who are not specifically trained in dealing with numbers and mathematics and statistics. But then hopefully from this short introduction to optimization, we can each take home something. And I'll try to go through optimization like in a step-by-step manner by following this very simplified workflow. And if I were to categorize optimization, I'll categorize it into two main categories. One is single objective optimization, where you only have one goal to achieve. And the next one is multi-objective optimization, which when essentially you have multiple goals, each with opposing nature in how you achieve it. And how do you decide on which one to choose? So I'll try to go through our thinking process through the use of this case study. So the very first step and the most important step is to define your problem statement. Essentially, it's by defining your objectives and defining your constraints. So first, I'll start with the constraints definition, which is essentially your geometrical parameters consideration. So for our roof design, we came up with 4 different parameters that we chose to guide our design. The first one being the spacing of arch set number 1, and for the second arch as well, the height of the arch, which is essentially the height of the dome, and the depth of this truss arch. So you can see from like the video how the different kind of parameters can affect the shape of the roof so much. And by shuffling and optimizing this geometrically, we can arrive to a solution that is gonna perform well while maintaining our design intention. And then the next one, which is equally important, is to define your goals. So the objectives, we started by considering 2 different objectives. First one is steel quantities, which is essentially the weight of the structures. So the heavier the roof, the more structures you have to put, the more steel, the more costly the entire project is gonna be. And then the second one is to minimize deflection by running our serviceability limit state. So this will give us the maximum deflection of our roof. And we want to minimize this deflection as much as possible. And then on the right column, we have our constraints, and our initial geometrical parameters are going to be part of these constraints, because through our definition of our geometrical constraints, you can guide the extent of how the shape is going to morph. So let's say the maximum spacing between the arches, the maximum height of the dome, the minimum height of the dome, that sort of stuff. And then in terms of performance, we want to try to limit the maximum utilization ratio of the roof structure. So essentially, we want to make sure that every single elements that is in the trusses, basically in the roof structure, they don't go over their limit, so that they don't fail. So after we come up with our problem statement, then we ask ourselves how many objectives, because essentially we want to decide whether we should go with single objective or multiple objective. Then in our case, we have 2 different objectives, which is to minimize weight and to minimize deflection. And then we need to ask ourselves, like, how are these 2 different goals behaving when you try to optimize one over the other? Are they gonna be moving in the same direction, or are they gonna oppose each other? And in our case, as we try to improve on the weight, which essentially we try to decrease the weight, so that means we're gonna put smaller elements in the trusses, it will deflect more. So it's a problem where when you decrease your weight, your deflection is gonna increase. So it's like a problem where you have 2 goals with opposing nature. Then it's always good to ask ourselves whether we really need those 2 objectives to be included into optimization, or whether we can turn like any of them into a constraint. In our case, when we deal with deflection, it's not really, we have to have the least amount of deflection as much as possible, but we just have to maintain the deflection so that it's within the allowable limit. So we choose to turn our deflection into constraints, and then we revise our problem statement. Now we have just a single objective, which is to reduce the weight of the roof, and then we move our deflection into our constraints. And then we go back to the start and ask again ourselves, how many objectives do we have now? So now we only have one. Then good, we can use single objective optimization. In our optimization scenarios, usually we try to push us to move towards single objective optimization because one, it's easier to rank your result because you only need to think about one goal. So when you make your chart or like tabulate your result, it's very easy to see which design performs better than each other. Because if you go to multi-objective optimization, then it becomes very difficult to figure out the necessary trade-off that you want to compensate between the different goals. So in this case, we can do single objective optimization. And what does that entails? So first, we set our parameters, design geometrical parameters. So in our case, if we were to exhaust the entire possibility, we would have to run 60 million iteration. And if we have the computational capability, by all means do so, then you will definitely find the solution that is the best out of everything. But then in most cases, we don't have the luxury of that and the luxury of time. So we have to narrow down the number of iteration, but at the same time, getting as close as possible to the best solution. So after we define our parameters, define our problem statement, which are the objectives and the constraints, we run our structural analysis for every single iteration run, which are essentially running cross-section optimization so that every single design is optimized, and to check for our maximum deflection and maximum utilization ratio. And all of this is going to be looped using the optimization solver. So for this particular case, we use Opossum, which is an optimization solver plugin in Grasshopper that also utilizes a surrogate machine learning model. So this helps cut down the number of iteration required for you to achieve your result. So it gets very close to the best solution with like fewer number of iterations. And then once you reach convergence, basically you are done with your optimization. And then if we take a look at the result, since it's a single objective optimization, the result is very clear in terms of its ranking because you can plot it with one axis being your goal, the other axis being the ranking. So the ranking from 0 to 100 something and the relative still weight being normalized from 1 to 1.7. And then what is another thing that is very important for us as designers is not to just take the result at face value, because as designers, in most cases, the best result numerically and like performance based wise is not always the best solution for our case because we have so many other factors to consider, like constructability and other stuff. So every time we run optimization, we always narrow down to recommendation being a few best solutions, which is then is gonna be further scrutinized within ourselves and like with the clients and the architects. So now if we take a look at the best 20 result and taking a look at the best 8, not really the best 8, but to exhaust the entire span by picking 8 different solutions, we can see how the geometry are actually very different, even though they perform in a very similar manner. So let's break it out even further. Firstly, let's take a look at the objective goals, which are our weight, and the deflection, which is our constraint. In terms of weight, they all perform awesome. Essentially, they are as good as the best. So all 8 has the same value. In terms of constraints, you can see like quite a big gap, but then constraint is not really for us to minimize. We just want it to be within a allowable limit. And all of these are within the allowable limit. So essentially all of our 8 solutions are good solutions. We can go with either one. And then after that is to see the different resulting geometrical parameters. So firstly, let's take a look at the spacing of the arches. You can see quite a big gap in the result, but then as we have seen earlier, they all perform equally nicely. So you can see the gap from 30 meters, 90 meters, and 150 meters. So that means you can be quite flexible with your spacing of arch. And when we take a look at the height of the arch, it's a zone within 25 and 42 meters. So as long as you're within this zone, you are gonna perform very well. And then when we take a look at the depth of the truss, almost all of them try to max out the depth that we specify, which is 12 meters. So as long as you have around this spacing of truss depth, you're good. So essentially, what can we learn from this optimization run? The first thing is we can be flexible with our arch arrangement because it doesn't really affect the final performance, as long as you maintain the structural system that is prescribed at the start. And then how high can your dome be, or like more like how high should your dome be for that performance to be within the efficient band? You have to be within 30 meters to 40 meters, and the truss depth should be around 10 to 15. So this is our recommendation that we give to the architects, and we discuss with them, and they give us our input. And through a series of discussions, we actually come up with the final design using the initial system that we have agreed upon. And then this is a short video that is which is the next step after we have finalized our design. And this will show how we use our digital toolset to actually create parametric models so that we can fine tune the design very easily, and we can discuss and make changes quite easily too, and how we can jump around between the different software so that we can cut down on the amount of very intensive labor work and to focus on the design. So at the start, after that optimization and the discussion with the architects, we receive an updated 3D model, which are basically just an envelope architecture model. So from this final envelope design, we came up with our parametric structural model so that we can better fine tune the final result of our structures. And at the same time, we can do more iteration and do more discussion with the architects. And it's very beneficial to have a parametric model that is clean and rationalized, because when we do our model properly, then it can be sent over to different softwares very easily. And in this case, we built our model in Grasshopper, fully parametric, using as few as possible of hard modeling in Rhino. And once we have all of our model parametrically in Grasshopper, we can move on to the next step, which is to refine our design in our structural analysis software, which is ETABS. So we developed a plugin, also using some third-party plugin to help us work very flawlessly between the two softwares to send over data and to receive data back. Also within our structural analysis software, we developed some custom script and plugins also to help us better refine our design in a more like automized manner. And this shows the final result of the roof structure, all within allowable limit, all sized properly and optimized. And then after we are done with the optimization, we bring back this data information into Rhino and Grasshopper so that we can update our parametric model and use it for visualization, or to eventually be used for our beam modeling. So Rhino is not really a beam software, it's not really structural engineering software, it's a geometrical software. So by default, Rhino doesn't allow you to attach data into its geometry. But then I use user attribute to attach data into the geometry, which then I can read from Grasshopper and send over to Revit using Rhino inside Revit. And then this shows how we have used the same data that we receive from ETABS and built the custom sections in Revit and send the geometry over. As you can see, the geometry looks exactly the same as the Rhino and the ETABS, and they're all basically the same model. It's just they morph when you go from one platform to the other. And then the good thing about working in Grasshopper is there is Rhino inside Revit nowadays. It's getting better. Not the best, but it's getting better. You can supplement it with a few of the Revit API functions, and it can do quite amazing things. In this case, we try to actually make drawings of all of these trusses, elevation drawing in Revit as Revit native elements through the use of Rhino inside Revit and a little bit of Revit API scripting. So as you can see, it might look a bit messy, the scripts, because I mean Rhino inside in the first place is not optimized for doing drawings. It does well in sending geometry over, but then to do drawings is still a little bit not so refined. That's why you have to complement it with some Revit API maneuvering. But you can see the result is actually quite neat and quite nice, and everything is actually automized. So every time we make changes to the Rhino model, we can straight away reanalyze in ETABS, bring the data back over to Rhino, and redo the entire thing, get a new set of drawings in like less than an hour, which is quite amazing. So with that, I would like to conclude with again our vision and to take a look at like through the case study what we have actually applied. So we always want to be able to deliver our vision as clearly as possible, our design, our intention. So that is through the use of geometrical rationalization and visualization, which can be seen from our use of parametric modeling and how we try to be as efficient as possible in our design by always optimizing our design using our structural engineering software and try to automate that so that we don't really spend too much time just modeling things over and over again. And we always aim to empower ourselves so that we can do more high level design and not spending our time on doing labor intensive work like remodeling things over and over again or go home earlier, right? And yeah, the pioneering part, always we try to be always forward looking and look out for like the best tools and the best knowledge that we can get at any point of time. And at the current time, we think artificial intelligence is getting more and more used, and the use in the AEC industry is getting more prevalent as well. So we are currently looking into that. But in terms of our use in our day-to-day use, currently still limited to our optimization, but we hope to be able to get more knowledge and I guess to open up ourselves to more things that's to come. And with that, I'd like to thank everybody for the time, and hopefully you guys learn a couple things from our presentation.
Okay, thank you, Giovanni and Samuel, for your presentation. I think it's quite detailed how they've shown us step by step what they're doing, all the different optimizations and the very, very neat geometry that you guys get eventually. There's a lot of troubleshooting to be done. Yeah. Okay, so I think we are taking some questions from the online Zoom. If any of you guys in the audience have questions, just feel free to raise your hand. And I think Wen Wei will go around and I don't know. Just if you guys got questions, raise your hand. Wen Wei will come and attend to you, and then he'll let me know, and then we'll address it. But other than that, okay, my name is Alvin. Yeah, I'm kind of like moderating this session. I guess we'll start with a few questions relating to maybe right from the start, Future Design Studio. How did you guys birth this team? I guess the computational designers is quite central to the role of Future Design Studio. But it must be a pretty new addition to the whole industry in terms of the whole scale of our don't know how many decades history. So just talk us through how did these guys come into play? Yeah.
I think so. Before becoming part of Ramboll, we were a different company, a different setup, and we had a certain vision and certain uh, design ethos. I think the founder of our company always spoke very loudly about fusion engineering, which is perhaps a better word of describing what I mentioned, bridging that gap between architecture and engineering. So few years back, I would say about 6 or 7 years ago, when we saw the opportunity with computational design, then we decided to jump on it, and we slowly created a team. Obviously, very few limited members at the beginning, but now the team has grown to a relatively good number of people. As I say, we're from different backgrounds. Sam itself is study architecture. We have data scientists. I'm an engineer myself, so we mix that up. As you say, that's really like we think important for the design for our industry to adopt and implement as much computational design as possible because of the things that you've seen on the screen. Essentially can make things better, faster, better for everybody.
Thanks. So you said fusion between architects and engineer. Do you see increasingly that this will be pretty much unavoidable? And we see even in NUS, they've merged both the architecture and engineering colleges together. So how do you see the evolution of the architect's role? Um, and are, does it mean that architects will be taking on more and more responsibility, or what? How do we make it efficient in that sense?
Yeah, I think that's an interesting debate to have, but I believe that architecture is a very specific requires a very specific skill sets. Engineering requires another skill sets. But I would think that as we're moving towards this more digitalized world, then definitely there will be more um, rooms for discussion. So essentially, if I look at it historically speaking, and in the past few decades, there has been quite of a distinction between architecture and engineering. And very often it's kind of opposing, right? There's always jokes about the engineer saying no to the architect and whatever. But we should probably try to move away from it and with what we call fusion engineering. So we come closer to you, you come closer to us, we understand each other, and we co-create something. I think that's what it should become. It doesn't mean that the architect has to take on more responsibility. I don't think the architect should. It's just about being able to communicate, speak the same language, and create something together rather than doing things sort of independently and in silos. When you look back at like centuries ago, again, I'm from Italy, so there wasn't a distinction between architect and engineer. They were one and the same, right? Over time, the two disciplines are sort of split into different schools, but I think it's important to come back together, not necessarily overlapping, but at least walking in the same direction, if that makes sense. I don't know, Sam, if you want to add something to that.
Yeah, you can just use that. Yeah. So yeah, and Samuel, maybe as you answer, you just talk us through how you embarked on this journey. Did you start from a computational background? Did you start from an engineering background? How do you get started? What were the challenges involved?
Yeah, I think in my case, I mean, I went to architecture school, so it's like I've been always around architects, and the way I think, I guess, is quite similar to architects. But then it's like once I started like diving deep into computational design, and I start to think whether uh I should call myself an architect or whether I'm not an architect anymore. It's like kind of identity crisis back then. Uh, but then I start to think, I guess like being architects is not so much about designing buildings, and also being like engineers is not so much about optimizing structures and just like doing number crunching. It's really about problem solving eventually, right? But it's just which part of the problem are you tackling. Architects tackling different problems than the engineers. And then as computational designer, uh I think of myself as in between the two. So because uh I can I can talk to the architects because I mean I'm trained in architecture. So I can help my colleagues to understand more about like the architectural intention, And then while preparing presentation or drawings, then I can help my colleagues also to present things in a way that us architects can understand or can appreciate better. So to me, it's really the shift of mindset from thinking that architects and engineers are just uh, doing their own things. But essentially, we are all designers. We are just problem solvers. It's just we are tackling different part of the problems, and wouldn't it be great if we can just collaborate and just share our thoughts and design together because we are essentially trying to achieve the same thing.
And what's the toughest part of it?
The toughest part of that is to satisfy both sides, I guess, because uh, well, I guess it's always the ideal scenario that we say yes to everything that everybody says, the clients, the architects, and the engineers. But then in most cases, we have to say no to many things, and to say no without actually just justifying is a little bit irresponsible. So in our case, we always try to not just say no, but to give guidance instead. So it's like to just say no is really, I don't know how to say, like like you don't really know what's happening and you just say no. But usually the right answer is not say no, it's like the right answer is you should do this instead or you should do that instead. Or at least if you wanna say no, we can't do that because this. So we try to always justify our actions and to as clearly as possible deliver like a solution which might not be the ideal scenario that architects had in their minds or the clients, but which we think is the right directions. And as consultants, which are what Ramboll is, we try to not always be. It's like we try not to always maintain a good image, you know. It's like sometimes you have to say no, you have to say no. If something is wrong, you have to say that is wrong. But then you can't just like blatantly say that it's wrong without actually justifying because in most cases when something is wrong it's like there is a better solution and you have to find that better solution before you actually like say no to the architects or whoever. So it's really about like answering properly and have proper understanding before actually communicate because sometimes we just can't understand each other that well.
Okay, so I think there are three words that he said that's very essential. I think if we take nothing else from this, we take that those three words. It's called just say no. You know? Which is true because as architects, you know, the more the industry evolves, the more architects take on the roles. You know, previously you take on the drafting role, then now you're taking on the computational design role, then next you're taking on the AI programming role. So there are some things that we just have to let go of as we take on more and more things, right? So that we can all go home early. Is that, yeah. Okay, so we have some questions from the audience. I guess mainly just two questions, unless there are more coming. Who came up with the shape, the general shape? Who sets the direction? Who came up with the original shape? And yeah, what's the roles involved?
Yeah, so typically, typically the architect would come up with the building, or in this case, that stadium overall shape. So we understand, and that's dictated by other things, right? The project brief and other stuff. So they will come up with a general shape for it, which is decided on certain basis. So first of all, we try to understand what are the bases that they follow to come up with that shape. And then we engage them in a conversation, whether there are rooms for it to be changed or not. So that's when we did the part that Sam presented, essentially. We start to look at it and question whether that shape is what it should be or whether it can be modified. As long as we justified with that process, so with that single objective optimization, we managed to find the ideal range of solution. We presented it to the architect, we communicated it with them. So that's all about the co-creating aspect of things. And they were happy to see that. Obviously, if you show them that things are working better, you're not disrupting their design or destroying it, you're just modifying it slightly, but it can work 20, 30, 40% better. Why not? You save money to the client, it's good for everybody. So then they would take that on board. they would adapt it to their shape, give it back to us, and then we implement it. So that first part to me is the most essential, which happens at concept or schematic, which is about that co-creation, right? You just don't get something from somebody and do it. You get something, you question it, you look at it, you twist it around, you come up with something else together, and then you do it. And you do it better by doing it that way.
So I guess that justification process is incredibly important because I think even for myself, we faced situations where the boss gives you a whole lot of options to
Yeah,
work on, and then they ask you, how do you know which is better?
yeah,
So then with
that's
the
all.
current software we
Yeah,
have, we show them, yeah, by numbers, this is better. It limits the steel we
yeah.
use, etc., etc.
And that doesn't mean that, look, this is one approach to it, right? This is optimizing an objective. For us, it's reducing material, reducing cost, reducing embodied carbon. There might be other objective as well, right? So this is just one way of looking at it from us. Somebody might want to add other objective to it, so we can add that on and develop it along that line. But at the end of the day, it happens, not in this case, but in other project, it happens that you develop the most efficient things and, you coordinated, the architect is happy, but the client doesn't like it. We have to move to another direction, even if it means it's not efficient, if it's more expensive. So like, it just doesn't, I think as Sam presented earlier, it's not just about looking at what results you get out of this. This is just a guidance for you to move in that direction, in the direction of efficiency, in the direction of excellence of design. Uh, but then again, there are other factors. Sometimes these options are picked up, sometimes they're not.
Which also means that as we go along this road, increasingly what I find important is to identify the goals
Yeah,
and to really clearly delineate what you're trying to achieve
yeah,
with every set of problems you're trying.
yeah, absolutely. Because I think, as he presented again, if you have too many objectives, too many goals, then it's pretty easy to get lost in it. Like you don't know whether the options you get out of it are actually satisfying all the goals or not. So being very careful about the goals and the parameters, it's essential. So that's a little graph that is shown. It was actually our thinking process. So at the beginning we had two objectives, but we realized that what we were getting out of it was a little bit, to some extent opposing. So we rephrased the problem and resolve it, and it was a lot better, and the responses were a lot more optimal and efficient. So you're right, being able to structure the problem in a very simplistic manner is essential.
Yeah, I think that pretty much helps in all aspects, not just down
Not
to
just these, yeah.
computational design, just fixed objective, fixed mindset, hit straight towards it. Everything else we discard or revisit once
Yeah.
we're done with the first objective.
Absolutely.
Yeah. Okay, the second question we have is so it's a little bit more abstract and future oriented. How do you see artists' role with computational design, future design studio? For example, Capital Spring, where you have cool little columns coming down at the ground floor and going up all the way. And I guess even Capital Spring, where the facade itself is pretty cool. Yeah.
Yeah, I think there is a significant overlap because I think what the first slide that I've shown in the beginning, I was showing some of the project we have done, and you can see sometimes they're stadiums, sometimes they're high rise, but we also focus on other things like more artistic, or rather, we're not artists ourselves. We don't have an artist on our team yet. We might have in the future, I don't know. But we assist artists to develop those things. So we provide a computational design aspect for them to implement their designs. So we've done, for example, in Malaysia, there was a series of artists doing a bamboo sculptures. So we did some computational analysis and we assist them with coming up with these crazy bamboo sculptures. Or once we did an origami hanging sculpture with a PhD artist in Malaysia, which was pretty interesting. So it also requires some computational analysis. So I think there are overlaps. At the end of the day, computational analysis is just using tools to do something. So we do buildings or structures, so that's what we use it for. We do environmental sustainable design, so that's what we use it for. But if you do art, you can use it for that too. Yeah.
Yes. Yeah. So thank you for your answers.
Thank
I'm for me, I'm quite happy with what you guys have shared,
thank you.
and it's very systematic way of looking at it. I think your responses have answered pretty much whatever I've had in my mind.
Yeah.
So if is any other questions from the yeah, sure. You just read them out.
Yeah. Y- Sorry, I just go to the screen. It's easier for me to read out. Okay, the first question is, there were a lot of different tools involved. Is it difficult to manage change? The designers need to learn and master them. Are they difficult to learn? So this is the first one, which means that there's a lot of variety of things. Or you want to answer this first? There's a okay.
Yeah, you go ahead. Yeah.
I think um, new tools will always come, and with like AI now, it's just gonna get even faster, right? The new tools that's gonna be available for us to use, and I think it's one thing is not really whether we want to use new tools, is whether we should use new tools, because one thing that is very important for us engineers is to make sure that our result is accurate. So it's not just any tools we can use for our design. We have to make sure that it's actually giving you satisfactory result. So when we try to adopt new tools, that means we have to do like quite extensive testing to make sure that we can get better or at least the same result. For example, when we want to do optimization, do we have to go to ETABS, I mean, our structure analysis software every single time, or we can do with like a not so extensive software only for optimization? So that has been at the back of our mind for quite some time, and we have been running testings. So that is on whether we should take on new tools. And in terms of difficulty in picking up new tools, definitely yes, which is why in our team we try to get people with different backgrounds so that we can at least augment each other, so that when we need to do different things, our rate of learning is gonna be faster also, because like some other guys might pick it up faster than me, let's say. And also I think we are very limited to what information we can get exposed to every day. And by having people from different backgrounds, we get exposed to tools that you might know actually exist. And this is when things get interesting, when you can actually use tools from other disciplines and apply it to your discipline. That is when you get very interesting design and very different design. Say when you try to apply AI to art nowadays, right, using Midjourney and DALI, that is when you get very interesting results. And how you can try to apply computational design to art also, how you can build things that initially can't be built, or you can model things that initially can't be modeled. So yeah, that is very interesting how you can actually learn from new disciplines. So I think it's like thinking about new tools is quite challenging. In a sense, it's quite a big hurdles that you need to overcome. But then if you think that it's worth it, and you have seen like these tools being used by other people, or you think that for sure it's gonna benefit yourselves, I think it's worth it to actually spend the time to learn new things, even though it's really out of our discipline. Maybe people might frown upon it at the start, but then usually like this kind of people who are trailblazers essentially, right, are the one that's gonna go very far ahead very quickly.
So the following question is, how do you manage these skills once the skill sets is being there, right? So, and you need to proceed to obtain other skills again. So this is the first one. Second one is, how do you manage change? If something change, right? So which means the designers, or how do you manage change? So this is the question. Change, and how do you manage the skills?
I think in terms of change, when you know if you look at the usual workflow in a normal building, there will be a lot of changes in the design, right? Especially early stages, which means that the process gets quite long and tedious. The architect come up with a design, the engineers engineer it, and then the architect change it. Then you have to go back from square one, rebuild the finite element model, rebuild drawings, redo the whole thing. So obviously changes is one of the critical um, things to be sort of mindful about during the course of a project. And that's some of the things that we try to overcome by adopting this workflow. Essentially, you can make changes a lot more seamless and fast. So it doesn't matter anymore. Like if we were to do this stadium 3 years ago, for example, it would have probably took us like months to develop that just the geometry and optimizing it. But with the new workflow that we now have developed, then it can be changed in a matter of a day. So you can change it tomorrow. Architect, you change your design tomorrow because you change your mind or you have a different brief. We can adjust it quite easily and get the whole workflow done very quickly. So in response to the question, changes, yes, are very, very something to be mindful about because they can make the whole design process a lot longer. But by adopting some of these workflows and digital tools, you can turn them around a lot faster. So they don't disrupt the process anymore that much. So that was the first question. The second one, sorry if I remember.
Uh, Second one is actually how do you manage your skills? Because there's many tools, so therefore there should be a lot of these skills.
Yeah.
And how do you manage them and to be carried out in as part of the digital workflow?
Yeah. So that's also very important because there is such a macro system of things out there, digital tool. You have the whole zoo family. You have so many AI stuff around now. I mean, people get lost in it, rightfully so, because there is really a lot. So you don't really have to use all of them. That wouldn't be uh, doable, but you just need to know what's around there, identify what is good for you, and master it and be able to use it very efficiently. But also, once you have done that, which I think over the years we have done it, so we have achieved that level of confidence with a lot of tools and we can do it. But at a later stage, you always need to invest in R&D. So dedicate some of your times in investing new stuff, in investing new tools, looking at what's out there. You explore some new tools, some may be good, some might not be, you abandon them and you move on. Obviously, we should not, learn everything, just learn what it's good for us and what can implement us. So that's what we do with the team. We targetedly select some new things that we find out there, investigate it. If we don't think it's going to bring any benefit, we just move on. If we think it does, then we invest time in it to develop it further and learn the skills. So that's our approach at least. There might be better ones, but that's what we do.
See, so thank you. So there's actually two more. One is actually from here. One is from me.
Right? Yeah.
The one from computer is actually, do you train your computational designers internally? So this is the
Yeah, so yes, actually. So we do train computational design internally. So we have built a team. The team had a core group of people that have very good computational skills, and then as we hire new ones, we pass these skills to the new people. So we invest in training. As I mentioned, though, we also hire people from different backgrounds. So sometimes they might bring new skill in. So our current staff learn from the new hires because they will bring new capabilities in. So that's how we augment ourselves. So we share and we train them, but they also share their new skill set with us so that the team can grow faster. But yeah, absolutely. I mean, being able to train the people that you hire is essential, whether they're computational designer or not. I think we should train the people we hire.
I see. So the one from me is actually with this all these new skills, change management capability. So as a client, will they exploit you further? I mean, they will make use of, oh, you can change so many things. Why don't you change more with, then they will expect more options from your side.
It is possible. I mean, it is definitely a possibility that expectations goes up. But that also means that as the client expectation goes up, it means that there is appreciation of what they see, which also means that you should be one that they select for their project. So it's already a good thing. Once you're in the project, then sure. I mean, if they want to exploit us, go ahead. We're happy about it. Yeah. The material.
Material.
Yeah. So yeah. So the materials one, yes. I mean, as engineers, we would suggest what materials are typically used in structure based on our, knowledge and engineering knowledge. For the specific case of this stadium, obviously concrete was not an option or timber wasn't an option, so the material was going to be steel. We knew it. But there are other projects where we explore different materials, sometimes timber, sometimes concrete, sometimes steel. Regardless of the material, what we do is we select the material, we select the option, and then we optimize it, which is what we've done here, to the element size, right? So that we can scrap off whatever is not needed, essentially, which is a good thing for the client because they save money. It's a good thing for the environment because you don't pollute that much embodied carbon. So, so that's the way sort of we go about it. Yeah. Yeah, absolutely. So, I mean, what we do, again, forget about this example because it was only steel, but for other projects, uh, a building, a tall building, you might have concrete option or steel options. So because of the material, they come with different cost, different pros and cons, different speed of construction, etc. And because of the options that they inherently have different benefits, right? So yeah, usually when we develop that, again, at the concept or schematic stage, we come up with a comparison of all the options, which also includes cost, material quantities, constructability, et cetera, so that the client or can have an assessment. Sometimes concrete structure might be cheaper, but they take longer to build. So if the client has a interest in building faster, maybe steel is a better option, although it might cost a bit more. It depends on the specifics of the project. But yeah, it's an analysis that we would offer so that the client can take an informed decision. Yeah. No, I mean, we are engaged by a client, so we should obviously satisfy the client vision and the client brief. But the client is not the ultimate client, is not our only client. We think we have a lot more clients to satisfy the society, nature, ourselves. So obviously what we propose, we have to be happy about, right? We have to be satisfied with ourselves. That's why we have those principles that we always try to abide to. We always try to sort of push for the most sustainable option, for the most efficient option. And we hope that the client can appreciate and understand it. If they have different perspective, that we'll try to convince them otherwise. But so yeah, it is a complicated, I mean, as you all know, right? Projects is not just one objective. You have so many. You have the client view, the architectural design intent, the cost, the constructability, etc. So it's about coming at the right balance to satisfy the most people involved. Not only the client though. They're important, but they're not the only one around.
Yeah, I think about balancing cost and design intention. I think at the start of the project, it's like usually you know what kind of space, what kind of building you want to design, and depending on the design of the buildings and the kind of space that you want, they say you want spaces for convention center, so no columns sort of design. So that kind of design prescription is gonna steer you towards a certain structural system. So you wanna go 100% on performance, on cost, you're gonna get design A, let's say. So we can design something like that. But then if you don't want things to look like that, means you are going further away from the most optimal design. That means cost is gonna go up. Is whether the increase in cost is something that you wanna pay for a better design. So it's not always on us whether we want to move away from like high performance design. Is whether the client or like the architects are willing to compromise on their design based on cost. So eventually it's all on us to to arrive at a single design that is in most cases are always a compromise from the ideals that all of us have in our minds, but always uh I always tell my colleagues and like the new hires, it's like as engineers they tend to look at like performance only. So look at numbers, right? Best numbers, best design kind of mindset usually when you just started. But I always tell them if it looks wrong, it's the wrong design. Even though the number says the best design, if it looks wrong, then it's wrong. If it looks ugly, then it's not the correct design. So I think it's really we have to turn on our designer mind, I think, like where the designer kept, and try to look at design holistically, because you can never satisfy everybody, and at most cases you can satisfy yourself, but then whether you can deal, you can compromise with it, and you can be happy enough with the design that you don't mind signing it and getting paid for it.
You have to use the tool, right? Don't let it use you. Yeah. So and I think one last thing is basically I just feel that also to answer Wenwei's question, I think it's not about mastering each technology, mastering each skill. It's more about mastering the language behind the skill. So if you can use Grasshopper, most likely you can use Dynamo. Yeah. And if you can use Grasshopper but you can't use Dynamo, that means something's wrong in your understanding of Grasshopper. Yeah. So that's the important thing. That's the key thing that you guys will be training your new hires and all these kind of things. So any last, yeah, sure.
So when you run optimization, right? So as the scale get bigger, then you need more like computing power in order to run it. So at this point of time, will companies end up investing more in like cloud computing so that they can get their iterations faster? Or how would that go?
Yeah, so that's one of the problems that we face when looking at especially multi-objective optimization. When you have a population of solution of 60 million over, it will take you forever to run. So either you buy, like a super huge computer, which is obviously a big investment, and maybe you don't use it that often either because you don't have this problem every day. Or you jump into cloud computing, which is something that we have looked into and we use at times when needed for special projects. I think is a good benefit because you pay per use, so you just use it when needed. You take advantage of the high computing power as much as you can, but without an upfront investment in the company. But at the same time, it's about using the tools, like for example, the genetic algorithm like Opossum, or there are others, that allows you to cut down the population from 60 million to a lot less. So you don't have to study all of that. So minor tricks can help you in reducing the computing power needed, reducing the number of objectives from 5 to 3 or whatever, you know what I mean? So being able to scripting or to phrase your problem clearly already would help you in reducing the computing power required by a lot. If you still require a huge one, then yeah, cloud computing would be definitely an option to go for.
Yeah, I guess that is the so-called brute force method, to go into just investing on more more computing power. But in most cases, based on my experience, I think you can cut down a lot of computing time by modeling properly. So let's say you want to run geometric optimization in Grasshopper, you can model the same thing in a million different ways in Grasshopper, right? You can script it, you can use the components, or you can utilize different set of components to achieve the same things. And to really know Grasshopper well, I guess, if you really want to dive deep into it, to know like which set of components are gonna perform better in doing the same things, that helps a lot. Because once I was required to design for something that is extremely huge, it's like when I use my normal workflow, it just doesn't work. It's not that it won't work, but it just runs forever and it takes so much time to just get an output out of the entire script that I need to rescript the entire thing just to get the same thing. It's sometimes it's not just about it runs faster with better scripting. It's sometimes when you come across project that is so big, your current script just won't run if you don't choose like the most efficient way of modeling. So again, I think it's to really polish your skills, I guess, polish our skills, and to know, like, to keep improving your modeling, I would say. And yeah, I would say in my scenario, I can survive without actually going to cloud computing.
Yeah, so that's the thing. Like we don't sell this service. Like you don't buy this. You, as a client, you buy one of our offerings, which are civil and structural engineering or, ESD consultants. Behind it, though, there is our support. So yeah. So if you remember that graph that I showed at the beginning, we have different offerings, consultancy offerings. We are the glue, or we like to think we are the glue that binds them together and enhances the product. So you don't directly buy our product, you buy our engineering products, our engineering services, but we develop these things to enhance our engineering services. So you by default will have better results and, optimal results, etc. Yeah, it could be quite honestly, like computational designing could be a thing on its own, like an offering on its own. I don't think is quite what we are about. Um, some of the discussion when we have with our teams, for example, we often develop some script, some apps and some plugins to help our engineer do their things faster. So the jump from there to produce something and sell it, it could be relatively easy, but that's not what we're about. We're not a software developing company. We're an engineering company. We do engineering. We just use these things as a tool to do what we do better. But it could be that somebody could use these things as an independent service, yeah. But not us. For us, it's about doing what we do better, and what we do is civil, structural engineering, sustainability, and so that's what we use it for.
Okay, so that's all the time we have. Thank
Yeah.
you so much for your responses. I think
Thank
they're
you.
very detailed, very in-depth. I hope they've answered all our questions. Yeah, we'll end the session for now,
Yeah.
and yeah, you guys just chill around here, talk shop, and yeah.
We'll chill around, yeah.
Thank you so much.
Thanks,
Thank you so
everyone.
much.